So last class, we talked about derivatives. And could anybody, by looking at our guided notes here, tell me what a derivative is? Gabby, could you tell me what a derivative is?
The derivative is calculating the instantaneous rate of change of a given function.
That's right. So using a derivative, we can calculate different functions and derive them, and we can use that in many real-world applications like finding acceleration or velocities of different things. But the one way we used derivatives in our last lesson was the definition of a derivative. And we just started talking about derivatives, and we're about to start with the definition of derivative, which is reviewed. Would you mind, Ben, telling me the function or the formula of definition of a derivative? It should be at the top of your notes page.
F prime x is equal to the limit of h to 0 multiplied by the quotient of f to the x plus h minus f of x all over h.
That's right. So this is the definition of derivative by its function. And what this is saying is we're going to take the limit as h approaches 0. So for every h in our function here, we're going to represent that as a 0. For the f to the x plus h is going to be our original function, and for every x in our original function, we're going to add an h to it. And then over here, we're going to subtract that value from our original function. And I'm going to show you that here as we do a quick review problem. So from last class, this is similar to what we've covered. So first problem we're going to try together here, as you guys will follow along with me, is f of x, 2x squared minus 16x plus 35. So if I ask one of you on the exam or at homework to take the derivative of this using the definition of a derivative, this is how we're going to go through it. And I have each step on here for you guys. And as a quick review, we're just going to go through it together, and I'll write it on the board as we go along. So step one. Josie, could you tell me what the first step is to do?
I don't know.
Look right
Oh,
under.
right here. Wait. All right, first step, factor 2 times x plus h squared.
Right, so we're going to put this into our formula. Sorry, that should have been the first step. And this is what it would look like if it was in our formula. I'm going to put this in parentheses so we know that we're going to later distribute the negative sign. So 2x squared, and this is where we're going to write our original function at. And we're going to leave in the parentheses all over h. So that's in the first step, like Josie said, is we're going to factor 2x plus h, and that's going to be 2x plus h squared. So we're going to factor that first here. And as you saw, it'll be x squared plus 2xh plus h squared. We're going to keep that in parentheses because we still have a 2 hanging out in front of it. And everything else is going to stay the same. Oops. Okay. Really long. Don't worry, we'll get to the short way around it. So what's our next step? Ben, could you tell me the next step?
Distribute everything on the top.
So right, so we still have this 2 out in front of what we just factored, and we still have the 16 and the negative in front of our original function. So I'm going to bring it up here, and we're going to condense this a little bit, and we're going to distribute it. Remember, we always want to include the limit sign, which I forgot here. The limit is h is approaching to 0, because that is important to tagging along with it. So when we distribute everything, it's going to be 2x squared plus 4x times h plus 2h squared minus 16x minus 16h plus 35 minus 2x squared plus 16x minus 35 all over h. So the next step, Cassie, will you tell me the next step that we're gonna use?
Cancel like terms.
Right. So to narrow this down and get rid of all this mess on top, we're gonna cancel our like terms. Chris, could you tell me which like terms we have on the top? They might be highlighted on your worksheet too. Under step 3.
2x squared and 2x squared, like the first 2x squared right there on the left, and then the 2x squared in between the 35, yeah, right there, yeah.
Right, yeah. These two are they're gonna cancel out because this is positive and this one's negative. All right, Joel, how about another common term?
You could cancel out the 16x, the negative 16x, and the positive 16x.
Right, that's gonna cancel out too. So what we'll get is then the limit as h is approaching 0 of, so we flip it over here, 4x times h plus 2h squared minus 16h over h. Alright, so that looks a lot cleaner now because we don't have all that hung together. Also, another one we can cancel is the 35. Those are gonna go too. So, what's our final step here before we can take the actual limit? Amy, what do we have to do next?
Cancel terms from the top with the bottom.
Right, so what we're doing is canceling the h's on the top and the bottom. So this first term here, we can take the h away with the 4x. The second one, we can take 1h away from the 2h squared. And the last one, we can take the 16h, which the h is just by itself. And the one on the bottom is all automatically gone because we only have one left. So our last step here is we can finally take the limit as h is approaching 0. So, knowing that h is approaching 0, we can plug 0 in for all the h's we have left, as we went over before. And if we do that, our final answer is going to come to 4x minus 16. And that's the derivative using the definition of derivative of this original function. Now, this all seems like a lot of work to do just to get that answer. And what now I'm going to go over, the power rule is a way we can condense this and even check our work of the definition of derivative. So I'm going to keep the answer right here in that last bit of work. Over here, we're going to start the power rule. So, the power rule is a really simple way to take a derivative of a polynomial. It is the easiest way whenever you're trying to derive a polynomial term. Other terms and techniques, if something's being multiplied or divided, it can get a little hectic and it doesn't always work out. But with polynomials, it'll work great. So, for instance, the power rule is just stating that if for every f of x, if we're looking to take the derivative of the original function, if we have an original function n of x to the nth power, what we're going to do is we'll make this a. For the derivative of that, using the power rule, we're going to multiply the exponent out in front with our coefficient here. So we're going to bring down the coefficient and bring down the exponent down to the front and multiply it by our coefficient value. The x is still going to stay there, and that's our variable in this case. And what we're going to do to the exponent now is just subtract 1 to it. And that's going to give us the derivative of the polynomial. So if we're dealing with numbers, for example, make this a little easier to see. If we have a function, let's say 2x cubed, all right? And we want to take the derivative of this, we're going to use the power rule, okay? So using the power rule, if we take the derivative, we're going to bring the 3 down in the front and multiply that by 2x, and we're going to subtract 1 from the exponent. And our final answer will be 6x squared. Because that, if we combine the 3 and the 2, we get 6, and 3 minus 1 is 2. So that is the derivative of 2x cubed. So, looking at that now, with that huge problem we just did on the right here, and we got the answer for it, if we go back and we use the same example, the same function we did originally, so if we plug in f to the x equals 2x squared minus 16x plus 35, the derivative of this, using the power rule, we can use the power rule in this case because we're only dealing with polynomials, I'm sorry. So taking the derivative of this problem, we will get 4x minus 16, and that's the derivative. What do you guys notice that is the same from this problem when we use the definition and the power rule. Josie, what do you notice is
The
between the
answer
two
is
answers?
the same.
The answer is the same, right? So for instance, if we're asked to use the definition of derivative, and it is a real long, hard problem, and we want to check our work just to be sure, we can always use the power rule to go back and check our initial work, because it should come out to be exactly the same if we did it right. So, another example using the power rule that we're gonna go over is f of x equals x to the fourth power minus 3x cubed plus 4x squared plus 21. So, if I'm asking you to take the derivative using the power rule, Joel, the first term here, what is the derivative of this term using the power rule? What do you think?
You would bring down the 4 to make it 4x to the third power.
4x to the third power. That's correct. Good job. All right, Gabby, how about the second term here? This negative 3x cubed.
Turn into negative 9x squared.
That's right. Because we're going to bring the 3 down in front and subtract 1 from our exponent. The last term here, Cassie, what about 4x squared? What is this going to turn into if we took the derivative of it? Now, taking the derivative using the power rule, we're going to bring our exponent down in front. So it would be like 2 times 4, and then we're going to subtract 1 from our exponent. 8x? That's right, it's going to be 8x, because what we're doing is we're multiplying the 2 times by the 4, and if we subtract 2 by 1 at the exponent, we're just left with 1x. So the x would just stay by itself, and that's saying the same as if it was just 1x here. So that's right. But we have this one term here at the end, the 21. It's gone. What happened to it? What do you guys think happened to this part of it? So this is considered the constant in the problem. Now, on our sheets here, it says what the constant is. So, Amy, can you tell me what the constant is?
A value that is not attached to a variable and is derived from deriving functions.
That's right. So because this is a specific value or a fixed number, it's not going to be included in the final derivative because we can't derive it any more than what it actually is. Because there's a variable attached here, we are able to break it down and derive it farther. But this is a specific value and it can't go any farther. Constants can come in as letters. They can be, for instance, pi. If this was replaced with pi right here, that would be considered a constant as well. As long as it's not the variable we're looking to derive in this situation, it is considered a constant. So, great job there. Let's move on to our next example. So example number 2 here on our notes, when we take the power rule, let's do f of x squared plus 4 to the square root of x plus 17. Chris, what do you notice that's different in this problem?
There's a square root.
There's a square root, right? Now this, you may think, puts a wrench into the whole problem and maybe the power rule isn't able to work. It doesn't work here. But we can rewrite that square root of x as a exponent. And does anyone know what the exponent of the square root is?
Is it a fraction?
It is a fraction. Do you know what that fraction is, Josie?
Come on, I made it that far. Give me credit.
Okay, I'll give you credit for that one. So if we rewrote that at square root as a fraction, it's going to come to be 4 to the x to the 1/2. That's the fraction of a square root as an exponent, plus 17. So, making it look like this is a lot more manageable, and now we can derive it, and it's just like the same way we did our previous 2 problems. So, Chris, what do we do with this first term here?
You put the 2, so it'd be 2x.
2x. Yes, that's right. Now, this term here is the same way, except we're just going to bring the 1/2 down in front of it. So, 4 times 1/2. We'll do it this way. What do we have 4 times 1/2? What's the answer to that? Margaret, do you know?
2.
2, right. So that's going to be 2. 2 is our coefficient for this one. Does anyone know, subtracting 1/2 from a 1, what is the answer to that? Does anyone know? What's that, Josie?
Subtracting a half. What was the question?
Subtracting
a half,
from a one. So
so it'll be a quarter?
1/2 from one, like this. What we're gonna get here is a negative 1/2 as our value. So we take a half from one, it'll turn to a negative 1/2. And the 17 is gone because what is it, Amy?
A constant.
A constant, that's right. So this is our derivative for this function. So, and that was my 15 minutes. So we're gonna skip to our closure here. I'm gonna hand around these whiteboards, and on them, I'm gonna write 5 functions on the board. I'm sure there one more. And for each one, I want you all to write the derivative and show your work for each of the function. So. First one we're gonna do 6x squared minus 4x plus 7. Need markers, right? That was my next question. How do you think you're gonna write them on the board? Chris was too quick. You're welcome. So the first one, 6x squared minus 4x plus 7.
Okay, we gonna have erasers?
Yeah, you can have the erasers too. I'm sorry. Give me another minute to work on this one. Alright, so Benin, first off, let's go ahead. Everyone raise up their whiteboards and show me what we have. Alright, good. Benin, what's the answer?
12x minus 4.
Right. Correct. Second one here. Let's do 7x squared minus x. So it might be a little trickier, but it's pretty close. Joel, what is it?
14x minus 1.
Right, 14x minus 1. Now, you might think this x goes away just in general, but since it's just x to the 1, if we subtract 1 from the exponent, we're left with x to the 0. X to the 0 is just 1. Any exponent that is 0, whatever the function is just 1. So that is why. Alright. 2x to the 4th minus 4x cubed plus x squared, or x, plus pi. Go ahead and give that one a try. Alright, go ahead and raise them up. That's right, Gabby, what's the answer?
8x cubed minus 12x squared plus 2x.
Right. We'll wrap up with this one as the last problem here. Alright, so how about this one? Square root of x minus 5x to the 3/5 plus 9. Challenge problem to finish. Right. Everyone wanna raise theirs up? Not quite. Alright, so some of you got ready. Joel, do you wanna give me the answer?
I got 1/2 x to the power of negative 1/2 minus 3x to the power of negative 2/5.
That's right. 3/5, if we take the whole number here, this is where some people have problems at. If we take the whole power and bring 3/5 down, bring that over here, times 5, the 5's are gonna cancel, so we're left with 3x. And then if we subtract 3/5 from 5/5, we think of 1 as 5/5, we'll get negative 2/5. And that'll be our exponent for that one. So don't forget to grab your homework on the way out, and I'll see you guys tomorrow.